So this is 5.1, and we're going to look at some exponential properties. The question we want to answer is, where do exponents come from? So maybe if we understand where exponents come from, we can understand some of these rules. So a long time ago, people were adding numbers together. What we're doing here is called repeated addition. So you're adding the same number to itself. 3 plus 3, that's 6. And 6 plus 3 is 9. And 9 plus 3 is 12. And 12 plus 3 is 15. We can think of this as being the fifth multiple of 3. So if you remember from elementary school what multiples are, 6 is the second multiple, 9, 12, 15. If I asked you to list off the multiples of 5, you'd say 5, 10, 15, 20, 25, 30, 35, 40, right? Those are multiples. Multiples of 3 are 3, 6, 9, 12, 15, 18, 21, so on and so forth. What we're looking for here is the fifth multiple of 3. People got really tired of adding the same thing to itself every time. This technique where you do this repeated addition, this is called recursive addition. It means that you take the last number and do something to it to get the next number. 3 plus 3 is 6. 6 plus 3 is 9. 9 plus 3 is 12. Another recursive series is the Fibonacci sequence. So 1, 1, 2, 3, 5, 8. How do you generate the next number? You take the previous 2 and add them together. You take the previous 2 and add them together. You take the previous 2 and add them together. So the Fibonacci sequence is a recursive sequence. So this recursive method of adding the same thing to itself, it works, but boy, it's slow. It takes a long time to do, to write out all these numbers. And so someone a long time ago said, let's invent a new type of mathematics. A new type of mathematics that lets us do repeated addition in one step. Instead of going 3 plus 3 plus 3 plus 3 plus 3, let's do repeated addition in a single step. And so out of that was born something called multiplication. And so you would start with a base, 3, and you would say, we would like to find the fifth multiple. Starting with 3, find the fifth multiple of 3. And that's how multiplication came to be. Multiplication means find the fifth multiple of 3. So in what? 2nd grade, 3rd grade, 4th grade, you started memorizing multiplication tables. Not because you can't add 3 plus 3 plus 3 plus 3. You could do that. But so that way you could do it more efficiently. Multiplication makes repetitive addition more efficient because you can memorize 3 times 5. And in 1st grade, all you did was add. You added and you subtracted. That's all you did. And then you evolved into maybe 3rd grade, where you started multiplying and dividing. And now you start doing repetitive multiplication. What's 3 times 3? 9.
27.
Times 3? 27. 81. 243. Not so easy, right? The numbers start getting bigger faster. Again, someone said, boy, this takes a long time. I wish there was a faster way that we could multiply the same thing by itself. And so a new notation was formed. Again, you have a base. You're saying, well, we're going to start with 3. And we already have this notation where it's like 3 times 5, so we can't use that. So how about we take that 5 and we superscript it? And we're going to call this an exponent. So exponents were born by taking a base, a number, and instead of adding it to itself, you multiply it by itself. What is 5 to the 3rd power in expanded format? Like if you were to write it out.
5 times 5.
Yep. 5 times 5 times 5, which is 125. 5 to the 2nd power. 5 to the 1st power. 5 to the 0.
1.
1? 0? It's 1? 0.
It's 1.
I'm not doing 5 times 0?
No, you.
I'm multiplying 5 by itself 0 times.
Yeah.
So what is that? Why? Pattern recognition. Check this out. How do I go from 3 to 2 to 1 to 0? What am I doing each step of the way? Subtracting 1. So to go from here to here, I subtract 1 from my exponent. Okay? And to go from here to here, I subtract 1. And to go from here to here, I subtract 1. So the pattern is and that left-hand column, you subtract 1 from each exponent. What do you do on this side? We started with 125. How do we get from 125 to 25 to 5? Well, again, what is the pattern? What are we doing from here to here? Divide by 5, right? Divide by 5. And then to get from here to here, divide by 5. So to get from here to here, what do we have to do? Divide by 5. And what's 5 divided by 5? 1. Let's keep going. 5 to the negative 1. Is 1/5 okay?
Yes.
Is positive 1/5 okay? It's a negative exponent. Shouldn't that make something negative? What are our rules? Subtract 1, divide by 5. 5 to the negative 2 is 1 over 25. 5 to the negative 3, 1 over 125. We're just following a rule. Decrease your exponent by 1, divide by 5. So speaking of rules, this little table that we made actually has 3 rules embedded in it. Rule number 1, anything to the first power equals itself. No matter what numbers you choose to make this table, I happen to pick 5 as my base and 3 as my exponent, but you could have used any combination of numbers. You will always get that row that says that number to its first power, that number to the first power is equal to itself. That's rule number 1. Rule number 2, anything to the 0 power is equal to 1. And again, no matter what numbers you pick, if you make this table and follow the rules, it'll always turn out that that number to the 0 power is equal to 1. Rule number 3 is a little bit more complicated. So I'm going to clear out some of this stuff. 5 to the third is equal to 125. 5 to the negative third is equal to 1 over 125. 5 to the second is equal to 25. 5 to the negative second is equal to 1 over 25. So 5 to the first is equal to 5. 5 to the negative first is equal to 1 over 5. What's the rule? If I had a over b to the k power, what is that equal to the negative k power?
B over A.
B over a. So this rule says that negative exponents reciprocate. They don't make the number negative. Instead, they reciprocate it. They flip it. They refliplicate. So negative exponents reciprocate. And this is an important idea because on the test, someone is going to get a negative exponent and they're going to make that a negative number. And it doesn't make it a negative number. It just reciprocates it. It doesn't make the number negative. And your whole math career, every time you saw a negative number, it made something negative, right? It changed its sign. Not here, not with exponents. Exponents don't behave that way. X to the m times x to the n. For example, if I had 2 to the third times 2 to the fourth, that is 2 to what power?
7.
The 7th power. I have 3 of them here. I have 4 of them here for a grand total of 7 2's. So if we were to write this, we would say x to the m plus n. This is called the product rule of exponents. X to the m divided by x to the n, m minus n. The numerator is the first number, the denominator is the second number, so make sure you get the order right. And guess what this is called? The quotient rule of exponents. X to the m raised to the n power. X to the power of m times n. So this is called the power rule of exponents. So you have a product rule, you have a quotient rule, you have a power rule. Now, like many math problems, there's about 3 different ways you could do this. What we're going to do is like the most efficient way, okay? Maybe the simplest way, the way that makes the most sense. What you're going to do is your eye is going to start focusing on different things. For example, there's a 3 and there's a 2. Here's a base A, here's a base A, and here's a base B, here's a base B. So you're going to start organizing this into like bases, base A and base B. That's one sort of category. And then also whole numbers. So what we're going to do first is let's simplify this by putting the numbers together. So now let's put the A's together. And then you put the B's together. So what we used is a combination of the product rule in order to simplify everything in the parentheses. Now we're going to use the power rule. This will become 6 to the second times A to the 20th times B to the 30th. Could you do this a different way? Sure you can. 3 squared A to the 18th, B to the 18th times 2 squared A to the second, B to the 12th. So that's distributing the 2 right from the get-go. 9 times 4, which is your 36. A to the 18th and A to the second is A to the 20th. And B to the 18th and B to the 12th is B to the 30th. So you could do it that way. Your eye is going to be drawn to whole numbers, things that are base X, and then things that are base Y. So you're kind of doing like 3 mini problems. All right, so if we look at the number part, that's going to be 24 divided by 2 times 6. I think that shakes out to be a 2. If we look at the X components, we got X to the 9th, X to the 3rd, and X to the 3rd. I think this is going to be X to the 3rd. For Y's, we've got Y to the 8th, Y to the 2nd, and Y to the 5th. Just Y, or if you really want to, you could say Y to the 1st power. You're identifying the numbers, you're identifying things that are base X, and then you're also going to identify things that are base Y. Do we want negative exponents? So let's talk about this. Let's do this one the same way we did the others. So that means we're going to put a 40 here, a 4, and a 5. And I don't think there's any argument that's going to be a 2. Right? 40 divided by 20 is 2. All right, let's do the x's. So we got an x to the 6th, an x to the negative 5, and an x to the negative 1. This is where we have a discussion and you have to decide what you prefer best. This is equal to x to the 6th divided by, and let's just simplify this bottom part and just call it a negative 6. How do you want to handle that? Now, we talked about negative exponents reciprocate, right? So what that means is you take this from the basement and you move it upstairs and you change the sign. I kind of informally call this the upstairs-downstairs rule. If you're upstairs and you move it downstairs, it changes sign. And if it's downstairs and you move it upstairs, it changes sign. So if you wanted to, you could take this x and move it upstairs and you would get that. Or you could say this is x to the 6 minus negative 6. That's what this leads you to. This leads you to x to the 6 plus 6. So what would you rather do? Do you want to subtract a negative or do you want to add a positive? It's the same answer. Most students will prefer to add the positives rather than subtracting negatives. And now we're going to do y to the 1st, y to the 2nd, y to the negative 2nd. And again, how you handle this is up to you. Some students are going to look at that 2 and negative 2 and cancel them out. They're going to make a 0, right? So that's just going to leave you with y to the 1st. Other students are going to take this negative 2 and kick it upstairs to make it a positive 2. So that'll give you y to the 3rd over y to the 2nd, which again, when you subtract, will give you y to the 1st. So I guess the final answer on this one is going to be 2 x to the 12th, y to the 1st. If I had 2x to the 5th, y to the 3rd, plus 3x to the 3rd, y to the 4th. Why can you not add these? These are not common terms. It's important to notice that these rules that we're applying, the product rule, the quotient rule, the power rule, are dealing with products and quotients. They're not sums and differences. If I multiply these, I can put this together, right? That becomes 6, x to the 8th, y to the 7th. If I take this exact same problem and I change this guy to addition, I cannot simplify. Why is that? In order to add and subtract anything, you need to have common terms. So for example, if I have 2 dogs plus 3 cats. You can't put them together, right? The answer is not 5 dog cats. You can't do this, right? However, if I had 2 dogs times 3 cats, what do I get? I get 6 dog cats, right? Or this is maybe a bad example, dogs and cats. Here's another one, 2 feet times 3 feet. And feet like the unit measurement, not like feet on the bottom of your legs, right? What do you get here? 6 feet squared. Feet times feet, right? Which is feet squared.